All right. Hello, everybody. My name is Jason Poff. I'm a PhD student here. Um, I use EPANET a bit in my research, and so I was asked to make a quick video kind of demonstrating EPANET and also going over this homework problem that you have right here, homework or 4.4.4, and this part 4 and 5, where you set up example 4.8 from the text in EPANET and check your solution with the software, and then also look at the pressure at junction F and see if your ideas for changing the network work. So I'll go mostly over part 4 and then show you how to look at the pressure at F, so you can test your ideas there. All right. So here on the right, I've opened up your text for example 4.8. It's this sort of simple three-looped pipe network. And on the left here is EPANET, the software, open source from the US EPA. It's very handy for modeling water distribution networks. That's what it's built for. It's pretty simple to learn, and so don't be too afraid of it. It's real easy. All right, so first, what we want to do once you have EPANet open is set up your units and sort of the project defaults, and I'm going to show you how to do that. So up here in your these tabs here, you'll want to go to project and defaults. So these defaults, let's see, let's first go to properties and then let's go to hydraulics actually. Okay, so looking at the units, we see here that we're going to be using the metric units. So everything is in meters and millimeters. And the EPANet is by default, it's American, so it uses English units of, gallons per meter and feet. So, but you can switch it to metric. So what you want to do is go to Project Defaults and Hydraulics tab here, and this stands for gallons per minute, and we're going to want it in liters per second, I believe. So this is LPS. So by clicking that, it changes all the other default measurements to metric. And so I actually pulled up the EPANet documentation so you can see that by going to, it's called EPANet 222. So that's the version that EPANet is on, 2.2. And this is kind of their documents here, this website, epanet.readthedocs.io. Super handy documentation. So I wanted to show you the units of measurement page, which basically says all the default units and what EPANet is expecting. So it's a little hard to see here. All right. So if you scroll all the way down to the bottom, it says that the US customer units will apply when you have flow set as CFS, GPM, or MGD, but it will use metric units when you're using liters or cubic meters. So EPANet only gives you the option to set your flow units, but it sets everything else off of that. So since we set our flow units to LPS, liters per second, automatically our diameter for our pipes is going to be in millimeters. For tanks, it's in meters. What other important ones? Hydraulic head is in meters, length is in meters. So this is important stuff to know because it doesn't tell you in the software itself. It just assumes that you know this. So this is important to always kind of read the docs and make sure you know what the program is doing. So with that out of the way, let's go back to EPANet. So we have our flow units at liters per second that we're happy with. Head loss formula. So by default, it is Hazen-Williams, which is HW. I'm not sure if you've touched on that yet, but it seems like here the problem wants us to use the Darcy-Weisbach equation because it gives us um, this roughness, factor of 0.26 millimeters, which is what you use for the Darcy-Weisbach. So let's change it to that. So that's D-W. Okay. So now we have the right head loss formula and the right units, specific gravity. Okay, all of these look good. These are for the iterative calculations that EPANET does, and it keeps going until it has accuracy within this factor, so we can leave that as is. That all looks good. Okay, so now that we've changed the units and the head loss formula, we should be ready to go. These defaults we can leave as is because we're going to change everything anyway. And then the last thing here, ID labels. When you create objects in EPANET, it automatically gives it a label, an identifier, and you can keep it really organized if you give everything kind of a unique prefix. So for example, standard is for junctions like J dash, and then it'll be a number like J dash 1, J dash 2, and that represents junction 1, junction 2. I'm going to leave that blank because we want to label them with these letters like it is in the example. For the reservoirs, I'll do R dash. But we won't have any tanks in this example. And for pipes, I'll do P dash, just for sake of clarity. It's kind of nice. Actually, I might, you know what? I'm just going to leave that blank. Well, I'll do P dash initially, and then I'll change it to, I believe, the example labels pipes as AB for the two nodes that connect them. So we're going to leave that as is there, and we won't have any pumps or valves or patterns or curves in this example. So I'm just going to do those two. This is not necessary, but it just helps with clarity. Okay, so I hit OK. We have our default set. We look down here on the bottom, LPS. So that's how we know we're in liters per second. We're in metric, so we should be good to go. Okay. Now we can finally start setting up the network. A lot of setup there. So over here in this toolbar here, you'll see these items. If you hover your mouse over them, it'll tell you what it means. So this one's add junction, this one's add reservoir, add tank, add pipe, add pump, add valve, and then add a label. You can put little labels on the map. So I'm going to first add a bunch of junctions to represent all of the junctions that we see on the diagram to the right. So I hit the junction, and now you can see my cursor is active on the network map, and I simply click to add these junctions. So I'm going to add junction A. I'm going to move over and add junction B, move over again, junction C. All right, so I'm just moving and clicking, pretty easy. I'm going to go back and do junction D, and then E, and then F. Okay, so now we have that basic rectangular structure. I'm going to add H and add G. Okay, so that's pretty easy. It's added our junctions. You can see in this browser window. Every time you add something, it shows up here. And then as you scroll through this list, it highlights what junction on the map. So it's pretty nice. So now that we've added all the junctions, we can add the pipes. You need to have, to create a pipe, you need to have two junctions at either end, or else it won't create a pipe. You can't just draw a pipe in nowhere. So now that I have junctions, I can go to this add a pipe tool and start drawing my lines, adding my pipes. So you have to click on the junction, and then it highlights it if you've hit it correctly, and then you have a little dash line, and then you have to draw it again on the other junction to create it. And you just keep going. If you miss, it and you click and you're not completely on the junction, it adds sort of like a pivot point, so you can add like curves. So now we kind of created a funky pipe. This is just for visualization purposes. It does not affect any of the hydraulics, but that just doesn't look that nice. So I'm going to delete this pipe. So if you go to select object here, and then now you have a cursor where you can select objects. I'm going to select this. I can right click and hit delete, or I can also go over here to this red X to delete it, or I can press delete on my keyboard. So a lot of options. I'm just going to right click and hit delete. Confirmation. Okay, we're deleted. And you can do the same thing with junctions if you accidentally created a junction you don't like. Or if you click and hold, you can move stuff around. So I'm going to put that back. And we're going to go back to adding pipes. And then if you double click, it automatically starts the next pipe. So it's a little bit faster in terms of creation. So I'm just going to add these pipes here. And then we have a pipe here as well. And then finally, oops. Okay. So now our network here is looking a lot like the example, which is great. You can see in this data browser, we're on pipes now, and it's labeled everything P dash like we set in the default, which is great. Junctions, it's just given them a number. We can change those. Okay, so now I'm actually going to try and label the junctions accordingly to what it has in the example. And so to edit properties of items, you'll need to have your select object cursor, click on the object and double click, and you'll get kind of a browser window where you can edit the properties of that object. Also, you can just go to your browser over here and double click on the one that you want to edit, or you can hit this edit button on the right here. So a lot of options. We're going to change all of the junction IDs to represent what it shows in the diagram, just because it will be much clearer. So I just hit junction ID, I put it as A. And these just have to be unique, because everything needs a unique ID. All right, so actually I'm going to want to see these. I want the junctions to be labeled on the graph. So to do that, I'm going to go to View and Options. No, so this gives me all the visualization options that I want. So I'm going to go to, you can set the node size, links, labels. So links are these pipes, but they can also be valves and pumps, but we won't have to touch on that for this example. So I'm going to go to notation and display node IDs. So if I hit OK, now on my map, it's going to show the node IDs. So that's nice because I can see which ones I still need to change. So I'm just going to double click, change this to B, and then just the boring part you can skip. I'm just going to change all of these to the correct name as shown in the homework problem. So I'm going slow on purpose because I know new software can kind of be tricky, but feel free to pause or fast forward if you're feeling totally comfortable. This is way too basic. But I figure it's better to over-explain than to under-explain. Okay. So now we have all of our junctions labeled. We have all of our pipes added. It's looking really good so far. So the next thing to do is we need to add a water source. So right now we've only set up the pipes. So it says in the problem, this is a little too zoomed in. Okay. All right. So it says in the problem that the water enters at A from a water storage tank on a hill. And it says the water surface elevation in the tank is 50 meters above the elevation of point A. Okay. So there are options to add a tank or a reservoir in EPANET. They're different because EPANET assumes reservoirs, the level never changes. So it's like a steady, constant source that'll never run out of water. Where tanks, you have to input, the diameter of the tank, and it tanks can empty and they can also be filled, because sometimes you want to model in more complex networks. You have a tank here. How often do you need to pump up water to it to provide enough head for the pipes downstream? So for now, in this problem, we just want to model it as a reservoir. It's the most simple, and that's what it wants here. So I'm going to click on this reservoir, add reservoir button, and I'm just going to add it kind of next to A. It doesn't really matter where you do it. So now it has a little R1, and it looks like a little reservoir as you draw it in like a problem. So it says it's 50 meters above the elevation of point A. So by default, all elevations for these junctions are set at 0. So if we double click, we can check that. Yeah, elevation's at 0. So all of these are at 0, so it's all flat. And then we have the reservoir at 50 meters. So we're going to click on the reservoir and add the elevation of it. So it calls it total head because that's how much head. It has 50 meters of head above your base elevation. So let's add 50. And again, remember that by default, according to the EPANET documents that I showed you, since we're in liters per second, elevation is always going to be in meters. So all we have to do is add 50. Okay, and that's really all we have to do for setting up the reservoir. We do have to connect the reservoir to the network, which isn't really shown in the example. So I'm just going to do connect it with a pipe there, and we can address that later. But so now we have a reservoir 50 meters above point A. It's connected. Point A is at 0 meters, and everything else is at 0 meters. So, okay, looks like we are almost there. So now we need to set up the pipe properties, the pipe length, the pipe diameter, and also we need to add these demands that it has. It has 3 demands, G, C, and F. So let's do that really quickly. By default, all junctions have 0 demand. So we're going to go to G, and it's at 100. So we go down to base demand, and that represents just the default average demand of the node. So we're going to add 100, and we're in liters per second. And in the homework problem, it does say everything is given in liters per second right here. So we're good. All we have to do is hit 100 for G, C. Let's go, it's 50. Okay, that looks good. F, double click, and 150. Cool. So just that easy. Pipe demands are now entered. We don't have to add the inflow here. That'll be done with the reservoir. All right, so now let's go to setting up the pipe properties. So we're gonna have to move to this table in the text, which gives you the pipe properties. Okay, so here's each pipe, the length and the diameter. So this is what we want to add. The length is given in meters and the diameter is also given in meters. But let's go and check again what units EPANET expects us. So length, let's see if I can find it. Here we go. Length is expected in meters, so we're good there. But diameter is expected in millimeters. Okay, so we're gonna have to divide by or multiply by 1,000 when we're entering the information in to EPANET. So let's just start going one by one, double clicking on these pipes and changing the units. So I'll show you a couple examples and then you can skip forward, but I'm just going to change everything. So length for AB is 300 meters. Diameter, so we want this in millimeters. So instead of 0.3, we want 300. Okay. All right. So length and diameter, we're good. Okay, BC, actually, I'm just going to go down by this table. So AD. AD is this one, double click, 250 for length, and diameter is 0.25, which will be 250 millimeters. So 250 as well. And then exit. All right, so you get the gist. It's a little repetitive. I'm having to go in manually and doing all of this, but that is what is required. 200. Yeah, 350 and 200. I'll show you how to edit multiple properties all at once, but all of these lengths and diameters are different, so we're just going to go one by one. So BC, we did that. BG, 125 and 200. Okay. GH is 350 and 200. Okay. CH is here, and that is 125 and 200. Okay. DE is here, and that is 300 and 200. Okay. We did that. GE here is 125 and 150. 125, 150. EF is 350 and 200. And HF, finally, last one is 125 and 150. Great. Thank you for bearing with me there. Actually, one more pipe here, connecting the reservoir to node A. It doesn't give us, this pipe isn't in the example. So we're just going to give it the same diameter as AB, which would be 300. And then for length, since it's not included in the example, and the longer the length, the more head loss we're going to get. We're just going to model it as a length of 1. So we'll experience a tiny bit more head loss because of that, but it won't really affect the results, and it won't affect the flow in the pipes. So don't worry about that. We'll just set it at 1 and 300, and you'll see we're going to kind of get the same results as the example. Okay. Sweet. So now we've set that up. There is one thing, a pipe property I forgot to set up, which is fairly important. So if we go into the property editor window for pipes, you'll see this starred asterisk property are the required ones. So the one we haven't done is roughness. Excuse me. And that one is fairly important. So what we want to do is go back to our problem description, and it does give us All pipes are aged ductile iron with an E of 0.26 millimeters. So that's going to go in this roughness property. So let's go back to the default units and check and make sure what units EPANET expects this to be in. So here's roughness coefficient, and we're using Darcy-Weisbach. Otherwise, it's unitless, but for metric, it expects it in millimeters, and it gives us in millimeters. So that's nice. That's easy. So let's go back, and this should be 0.26. So all pipes are aged ductile iron. I don't want to go one by one and enter that. So I'm going to show you how to do a group edit. So first we need to form a selection window to show what pipes we want selected. So there's this select region tool you'll click. And then by clicking, you'll be drawing a bounding box. So everything within the box will be, well, every item, every object that is fully contained within the window will be selected. So you have to make sure to fully get everything in that you want. And you can end this by right-clicking, and it automatically finishes. So now that we have our bounding box, we're going to go to Edit and Group Edit. I could also have done Select All. That might have been easier. But so Group Edit, and then this window pops up. So it wants you to select what you want. So you can either do junctions or pipes. We're going to do pipes. So for all pipes within the outlined area, we're going to replace and then roughness with, and it's 0.26. Okay. And then you can also do more refined things. So like you can filter, so you can do width, like I only want width diameters below, this amount, but we don't need that. We can just do everything, replace roughness with 0.26 and hit OK. And it tells you how many pipes are updated. All right, so just click to get rid of the selection window. And let's double check. And look, all of our pipes are updated with the correct roughness. So we're good. Okay, finally, we have done everything now. So our next task is simply to hit a button and run the simulation. So for the EPANET, you can do a steady state or single time simulation, so it only simulates it for one time step, or you can do extended period analysis where you're looking at how the flows change over a day or over 3 days. We're just doing a steady state simulation. So let's go again to project and analysis options. Oops, sorry, that's not what I wanted. Okay, forgive me there. Actually, so in your data browser, go to options and then times. So by double clicking on that, it brings up sort of your time option window where you can edit how long it runs for. By default, it's set for a steady state simulation, so total duration of 0. So it's just going to run it once, and that's what we want. I just wanted to open the window to kind of give you an idea of where you can edit that information for future. So yeah, all right. So we're good to go. So this little lightning bolt is your simulation button. So yeah, so we're just gonna hit run. And then it runs the hydraulic simulation and it says it was successful. And here it says your time of analysis, day 1, 12 a.m. So that's the only time that it ran for. So in the browser window, this data tab gives you, access to all your data. If you click over to map, it gives you access over what properties you can view in your map. So for nodes, now that we've run a simulation, it has calculated all the pressure. So for nodes, we want to look at what pressure it is. So as soon as we clicked on that, it gives us this color code. And if we hover over the junction, it tells us what pressure it is. And it gives us in pressure in head, and pressure in meters. So, and it gives us those little color codes. So you can see at F, we have pretty low pressure compared to all the other ones. For links, let's look at flow. So we're going to hit flow, and now we have another key and more colors. So by hovering over, you can see what the flow is in liters per second. You might notice a few negative flows. Like in this one, pipe 7, it has negative 95. What this means is when I created the pipes, you create them with a starting node and ending node. And EPANET expects that the flow will go from the starting node to the ending node. And the negative tells us simply that instead of going from D to A, this is going from A to D. So it doesn't really matter. Well, it matters if you're having check valves and stuff in these pipes, but for our purposes, it really doesn't. You can see it's starting D and going to A, and it went the other way. So if you right click and hit reverse, it'll change the pipe. So now it starts from A and goes to D. And if you rerun the simulation, now we're going to have a positive value because it is going from A to D. So that's not necessary. You can also, if you go to view and options and flow arrows, you can put little arrows. Let's make them big. Build. So now look, there's little arrows showing you what direction the flow is going. So that's sort of fun to do. All right. So our task was to check the flows in these pipes and see if they match with our results that we got. So I'm going to scroll down to the results. The results are here in this table. So we need to check the flow that they got with their method and the flow in EPANET. So you can check all the results just by hovering your mouse. And you can also do it by generating a table. So this table button, if you hit table, it wants to know whether you want a table of nodes or links. And again, links represent basically the lines, and nodes are the circles. It says nodes and links instead of junctions and pipes because links can be pipes, but they can also be pumps and valves. So we just want links because we want the pipes. And then here you can kind of filter what you want in the columns, and then further filter if you don't want to see certain types of pipes, but we want to see everything. So we hit OK, and it gives us our table. So now we can compare. I forgot to change the names of the pipes to match what is in the table, so I apologize. What we can do is go to view options, notation, hit display link IDs. Okay, so now we can see on the map so pipe 1 is AB. So let's compare 205, 204.98. So yeah, looks correct. Pipe 2 is BC, 80, 79.72. Yep, that looks correct. BC, I'm just gonna go one by one. AD 95. Yes, we did BC. BG 125. Yep. so these all look really good. So looks like we got the same results. DE 95, yep. Let's look at HF 63, 62.81, yep. So this is great. 87 for EF. Yes, 87. So we're doing awesome. This got exactly what we got using the hand method, and this is what we would expect. So very good. Final part is checking the pressure at F. So you can see it gives the pressure at F as 16.22 in meters. And so to convert that to, it gives us, I think, kPa, kilopascals. Yeah, kPa, 85. So it needs it, the required pressure is 185 kPa. Okay, so to convert meters to kilopascals, you can just do this conversion here. It has in the bottom, so water, this specific weight of water in Newton per meters cubed for whatever temperature it's assuming water is. So all we have to do is multiply our pressure at F, which is 16.22 by, and then we want it in kilonewtons because it's going to be in kilopascals. So we're going to do 9.79, and it gives us about 159 kilopascals, and they get about 167. So our pressure that we calculated is a bit lower than what they calculated, which sort of makes sense because we have a little bit more loss since we've modeled a pipe that is coming from the reservoir into the system. So that includes some loss that isn't represented in their calculations, but it's pretty close within 7 kPa. So yeah, so the last part is just changing whatever you want in the network, rerunning the simulation, and then seeing if you get an acceptable pressure at F because that is too low. And I'll leave that up to you to do. I think you have the capabilities now to do that. This video was rather long for a simple process that I think you could set up within 5 minutes. So yeah, hopefully this helps with EPANET. It's a great tool. I encourage you to keep working with it, playing around with it. And yeah, so thanks so much. You can let me know if you have any questions. All right, bye.